Properties of rational exponents and radicals, part 3. We're on example 6, simplifying variable expressions. All right, so as you can see, A part says the cube root of 64 y to the 6th. So now we're going to have variables under the radical, so there's a couple rules that you have to keep in mind. When n is odd, that means your index and exponent, when that is odd, then you can have both a positive and a negative answer. So you don't have to worry about anything when n is odd. But when n is even, like if this is a square root and something's squared, okay, there are two possible solutions here. So the fourth root of 3 to the 4th power equals 3, and the fourth root of negative 3 to the 4th power also equals 3. So you can see there's two different answers here that produce the same number. So because of that, when n is even, you have to put the variable that you're working with in absolute value. Now, we're only going to work with this briefly. On the EOC, most of the time it says assume all variables are positive. If it says assume all variables are positive, that means they're not making you worry about this rule here. You may have to do it, I don't know, but usually it's going to say assume all variables are positive. But anyways, let's look to see how you do it if you don't know the variable is positive. So cube root of 64, if we come down through here, we can see that 4 cubed is 64. So we can rewrite this as the cube root of 64 and the cube root of y to the 6th. The cube root of 64 again is just 4. And then the cube root is the same thing as something to the 1/3 power. So you could rewrite this as y to the 6th times the 1/3 power. So 1/3 of 6 is 2. So you're just going to have y squared as your answer there. Now, we don't have to worry about absolute value in this case because anything squared is positive, and this is not underneath the radical sign. So for this one, you're going to have 4y squared, and you're done. Now, B part, we have a fourth root of x to the 4th and over fourth root of y to the 8th. So we're going to have fourth root of x to the 4th over fourth root of y to the 8th. And you can rewrite it if you want to. You don't have to, but it kind of breaks it up to where you can look at it individually. So the fourth root of something to the 4th power is going to come out as just that. So it's going to come out as x. Because my n, or my index, and my power here were even, 4 is an even number, I'm going to put x in absolute value. And then the fourth root, I'm going to rewrite that. That doesn't really look like a fourth root. It looks more like it's being multiplied by 4. So fourth root of y to the 8th. Again, fourth root is the same as 1/4 power. So y to the 8th times the 1/4 power, or 1/4 of 8, is just 2. So this is going to be y squared. So again, both of those went into that evenly. And again, anything squared will end up being a positive number. So you don't have to worry about absolute value or anything in that case. Example 7, writing variable expressions in simplest form. Write each expression in simplest form. Assume all variables are positive. So see, very quickly they went to assume all variables are positive. So that's what you're going to see most of the time, which means we don't have to worry about the absolute value. We're going to assume that they're positive. So we're going to have, let's rewrite this as a fourth root of 16. So I'm going to write all numbers that are perfect fourth roots, variables included, under the first radical. So I'm going to have a, let's say to the 4th, even though there's 7 here, I'm going to break this down into 2 parts. And then b, I can take 8 out of that because 4 goes into 8 evenly, and I'm going to have some left over. And then c to the 4th. And then I can multiply that by everything that's left. So I'm going to have fourth root of 16 is taken care of I brought 4 of the a's down, but I have 3 left over. And then I have 8 of the b's came down, but I have 3 of those left over. And then all of the c's came down. So now what I know is that everything in this first radical, this fourth root radical here, is going to come out evenly. So it's going to be all numbers or variables with no radical. So the fourth root is 16. If you remember, that's going to be 2. 2 to the fourth power is 16. Fourth root of a to the fourth is just a. The radical cancels the power. 4 goes into 8 twice, so it comes out as b squared, and 4 goes into 4 one time, so it comes out as c. And then we have times fourth root of. None of these are perfect fourth roots, so it stays underneath the radical. So that's going to be your simplified version doing that. So what we did was use the product property here to rewrite this one expression into 2 expressions, just so that we know that this whole thing is going to come out from under the radical. All right, B part says x over cube root of y to the 8th. Okay, when I see this, I know that I'm going to have to rationalize the denominator. Now, if this were a 9, 3 would go into 9 evenly, and the radical would go away. It's not a 9, but we can easily make it a 9 by multiplying it by cube root of y to the first power. Remember, anything we do to the denominator, we have to do to the numerator as well. Anything divided by itself is 1, so we're essentially multiplying this expression by 1 just to manipulate it so that we can rationalize the denominator. So that leaves us with x cube root of y on top. And on the bottom we have cube root of y to the 8th and cube root of y to the 1st, which is the cube root of y to the 9th. Cube root of y to the 9th is just 3. So I'm going to have x cube root of y over y cubed. All right, so for C part, we have a lot going on here. We've got numbers and variables, so let's just look at one part at a time. So we've got 14 divided by 2, so we know that divides into 7. And then we have an x to the first power over an x to the 3/4 power. All right, so remember when we have the same base, when we have a quotient, we subtract from top to bottom. So this is assumed to be a 1 exponent on top. So x to the first power. So we're going to do 1 minus 3/4. Again, having a common denominator will help. So let's do 4 over 4 and then minus 3/4. All right, so all I did was write 1 as 4 divided by 4. Hopefully we all agree that 4 divided by 4 is the same as 1. Then we're going to look at our y's. So we have y to the 1/3 on top. There's not a y on the bottom, so we don't have to worry about that. And then we have a z to the -6. So z, since the z's on the bottom with a negative exponent, it's kind of like -6. What we have to do is move that to the numerator and it becomes positive. So I'm not losing that negative sign. What I'm doing is just taking it off of the denominator here. So now we're going to have 7x. 4/4 minus 3/4 is going to be 1/4. And then y to the 1/3. It's already on top. It's positive, so it stays on top and stays positive. And now z to the 6th has moved to the top. So we no longer have a fraction. Okay, again, we're just using properties of exponents, properties of rational exponents combined with properties of fractions. Last example, example 8, adding and subtracting variable expressions. Perform the indicated operation. Assume all variables are positive. All right, so remember before I said this is kind of like adding like terms. You're just adding like radicals. So both of these have a square root of y. So we've got 5 square root of y plus 6 square root of y is going to be 11 square roots of y. And remember, when there's no index, it is assumed to be a square root. And if they already have like radicals, that's simply all you have to do. B part has a few more steps. We've got 12 cube root of 2z to the 5th minus z times the cube root of 54z squared. So these are not like radicals right off the bat. The first thing we need to do is pull out any perfect cubes. So let's start with the first part, 12. And then we've got cube root of, and the first thing I'm going to do is rewrite this as a product and only put down what's going to be perfect, what's going to come out perfectly with no radicals left. So I'm going to rewrite this as z cubed and then times cube root of 2z squared. And again, all I'm doing is using our properties of exponents, z cubed times z squared, same base, add exponents, z to the 5th. And I still have the 2 here. Now, why did I do that? Because this one's now going to cancel and leave just z. So I'm going to have 12z times cube root of 2z squared. Now, that's only the first part I've broken down. So I need to now do the same thing to the second radical. So I'm going to have minus z. That's already there. And then the cube root. Again, I'm only going to put the numbers that is a perfect cube to begin with. 54, I know 54 is 27 times 2. 27 is 3 cubed. So I'm going to put cube root of 27 and then times the cube root of 2z squared. And 27 times 2, again, is 54. So all I did was rewrite this expression here. I've still got the z, I've still got the cube root of 54, and I've still got the z squared. I just rewrote it as 2 terms. Now I'm going to have minus, this is z, times the cube root of 27. Cube root of 27 is 3, so that's going to be 3z. Again, I like to put my number first. You don't have to. And then I have times the cube root of 2z squared. Now you can see that the cube root of 2z squared, now those are in common. So the fact that these are now in common, that's what we were hoping, so that now we can combine like radicals. Now we can add those together. All right, so now we have 12z minus 3z. So 12z minus 3z is just going to be 9z. And then this stays the same. So cube root of 2z squared. And that is our simplified version for B part. So that one is a few more steps. Again, you just have to get familiar with your perfect cubes and how to break these apart and bring them down. But once you get to this part, you're simply adding like terms or subtracting like terms. 12z minus 3z is 9z, and then your like radical just stays the same. All right, that is the last example. If you have any questions, let me know.